discussion will consist of the design of a synthetic ammonia production plant. This was done as the Chemical Engineering 470 design project at the Pennsylvania State University. We are Team 32, the Ammonia Masters. My name is Erin Grills, and my team members are Alex Shield, Ryan Fox, and Mears Catamount. The plant will be built in Philadelphia, PA. This location is in good proximity to the Delaware River and access to rail and ship transport. The natural gas is fed to the plant via pipeline at 35,454 pounds per hour at a temperature of 80 degrees Fahrenheit and a pressure of 400 psia. The natural gas is a mixture of many different components, as you can see in the pie chart, including methane, nitrogen, carbon dioxide, water, and other contaminants. With this given feed conditions, the plant is competitive with other current ammonia production plants in the United States. This presentation will focus on the process overview represented by block flow diagrams. Next, the ammonia synthesis product specifications will be examined based on the process, environmental, and safety regulations set forth for the plant. Finally, the economic evaluation of our plant will be discussed. The overall production process can be represented by four main phases. Phase 1 represents gas purification and encompasses mercury and sulfur removal. Phase 2 represents hydrogen production via steam reforming and carbon oxide removal. Phase 3 represents methanation and dehydration, which prepares the process stream for ammonia synthesis. Finally, Phase 4 represents ammonia synthesis, where ammonia is produced and separated to purified sellable product.
Phase 1 is composed of three separate processes. First is mercury removal, followed by sulfur removal, and then air separation. During mercury removal, mercury is separated from the natural gas feed through absorption onto carbon molecular Cs. This method removes over 99% of the mercury, which is corrosive to downstream equipment. The process stream is then fed to the sulfur removal unit, which utilizes the Claus process. During this process, a stoichiometric amount of oxygen is fed to the burner, which oxidizes a portion of the hydrogen sulfide to form sulfur dioxide. In a subsequent series of 3 reactors, the remaining hydrogen sulfide and sulfur dioxide are converted to elemental sulfur and water. Sulfur undergoes a treatment process where it is then sold as a byproduct. Finally, the air separation unit provides oxygen for the sulfur removal unit and also nitrogen downstream for the ammonia synthesis. Air is fed to a series of 2 cryogenic distillation units in order to obtain pure oxygen and nitrogen streams. Phase 2 is composed of 4 separate units. Purified natural gas from Phase 1 enters the steam reformer, which relies on high temperature operation to convert hydrocarbons to hydrogen-rich synthesis gas via steam addition. 2 shift converters follow that rely on the water gas shift to increase the hydrogen production while lowering the carbon dioxide content, which is formed in the steam reformer. The high temperature shift and low temperature shift utilize 2 different temperatures and catalysts to maximize hydrogen production. Remaining carbon dioxide is removed via cryogenic separation unit, which produces carbon dioxide at a purity of 99.9%, which is then sold as a byproduct. During Phase 3 of methanation, in order to reduce the oxygen content downstream, an additional methanation process is used to convert remaining carbon oxides to inert methane. It is important to minimize oxygen content in the process stream to Phase 4 because of the potential combustion, safety hazards, and poisoning of the synthesis converter catalyst. Following methanation, the dehydration unit removes the remaining impurities in the stream while drying the gas stream for ammonia synthesis. Dehydration is done using a cryogenic separation. The key here is impurities in water are removed to prevent lowering the purity of the ammonia product because these components would drop out in the liquid phase ammonia during cryogenic separation in the following phase. Phase 4 consists of 2 processes: ammonia synthesis and ammonia purification. Ammonia purification utilizes a high temperature and pressure Haber-Bosch process to convert hydrogen and nitrogen to ammonia. Following ammonia synthesis, a cryogenic liquid vapor separator is needed to drop out liquefied ammonia product. The tail gas is recycled to increase the yield of the product, whereas the purge stream is needed to reduce the buildup of inerts.
It was determined that the plant capacity exceeds all target product specifications. The minimum specified target capacity for this production plant was 55,000 pounds per hour of ammonia product. Our plant was able to exceed this specification, resulting in 70,000 pounds per hour of ammonia. This is an overall increase of 27% from the minimum specification, with an increase of $21 million per fiscal year. Along with the increased capacity for the purity of ammonia, we were able to exceed the minimum target purity for the ammonia. The minimum target purity was 99.5%, and we were able to increase this purity by 0.2% to 99.7% purity of ammonia. This difference can allow for small process deviations that could affect purity, but the product would still have to be at a sellable specification. Future research can be conducted to determine if the product can be sold at a higher value for the pure specification, which in turn would increase the possible profit margin.
After completing an entire plant design of the ammonia plant, we generated the capital estimates for our plant. The inside battery limit estimates included the direct installed cost for process equipment and totaled to approximately $42.8 million. After further looking at the breakdown of the inside battery limit cost, the majority contribution comes from phase 1 and 4. This could be explained by the cryogenic nature of the equipment installed at those stages. In order to generate the outside battery limit cost estimates, our team looked at the previous bids and scaled the actual costs from that information. Accounting for environmental, site development, material storage costs, as well as the utilities equipment. The total outside battery limit cost was calculated to be $77.5 million, and the majority of which was coming from the raw material storage cost. Our team further looked into the operating costs of the plant, and the pie chart on the slides illustrates the main contributions to the ongoing costs, or the operating costs, coming from the utilities costs, from raw material purchases, as well as the fixed costs, which essentially includes the labor, the maintenance, the property tax, as well as the insurance. The majority of the operating costs amounts comes from the utility costs, about 73%. And this could be explained by further breaking down the utilities costs. And you can see that on that pie chart. More than 90% of the utility costs resulted from the refrigeration and cryogenic units using our main refrigerant R728. Overall, these utilities costs amounted to 8.6 cents per pound of final ammonia, compared to the overall operating cost of 13.7 cents. Combining the previous capital estimates of outside battery limits and inside battery limits, as well as operating costs, our team generated the cash flow projections of the plant as part of the economic evaluation. Critical assumptions have been made, such as 9% discount rate, 35% income tax, and 2% inflation, as well as other parameters which are represented on the table on that slide, the table above. Given a selling price of the final ammonia product of 17 cents per pound, our economic evaluation yielded $6 million positive net present value over the span of the next 15 years, which is the plant is expected to operate. The plant shows a positive cash flow projections, except for the first 3 years when the capital expenditures are incurred as a result of purchasing this equipment. And the result is basically depicted on this graph. In order to calculate the ideal 15% after-tax rate of return, we calculated a net back product price of 19 cents compared to 17 cents in the base case. And the NPV resulted to be more than 10 times as much compared to the base case. Our team further looked at the raw material prices to understand the economic evaluation of the project. The majority of the raw material cost amounted from the natural gas, which is contributing to 74% of our raw material cost. The natural gas price dictates the raw material cost of ammonia production and is clearly seen to be relatively stable, even though it has an erratic character. After looking at the historical price trend.
From the historical market trends of ammonia and natural gas prices, we recommend building this ammonia production plant. Since 2008, there was a small margin between ammonia and natural gas prices. This margin has increased due to the price of natural gas remaining relatively stable, while ammonia prices are predicted to increase. United States presence in the ammonia producing market is also smaller compared to other countries. Since our country's consumption of ammonia is larger than its production, there is a demand for US-based ammonia plants. Our main concern for our plant is to reduce the utility costs that can lead to exponential growth of the plant's NPV. As you can see, we have tested our base case utility costs and we have reduced them to 15% and 30%. In doing so, we were able to increase our ATROR and our NPV. Recommendations to lower utility costs can be done through the replacement of cryogenic units. A flash separation unit can be used for the ammonia and water, which will reduce the refrigeration costs for the heat exchangers. This will indirectly reduce the capital costs of the plant. Pressure swing absorption can also be researched to help replace the cryogenic distillation units for N2 and O2 separation. An alternate design for our dehydration unit from our methanator can also be used, utilizing triethylene glycol instead of the cryogenic unit, which uses refrigerants. This would be done through an absorber and stripper column combination. Overall, we believe that based on the discussed analysis, it is economically feasible to move forward building the plant at this point.